Welcome back to our supply chain management series. In this third session, we delve into the critical topic of supplier selection to guide you through this complex but fascinating aspect of supply chain management. Let's briefly revisit our journey so far. In the first two sessions, we laid the groundwork by discussing supply chain fundamentals, focusing on inventory management and the implications of holding costs. We also explored key metrics for assessing supply chain performance, such as turnover rate and weeks of supply. Additionally, we touched on strategic considerations like outsourcing and vertical integration, highlighting the shift from the highly integrated operations of historical companies like Ford to today's trend of outsourcing and system integration. Today, we turn our attention to selecting suppliers, a process pivotal to managing costs and ensuring the quality of inputs in our supply chains. We'll explore practical, data-driven methods for making these critical decisions, emphasizing their relevance and applicability to real-world scenarios. This slide narrows to a singular but substantial topic, employing a total cost approach to select the best supplier. This methodology is not only comprehensive but also intricate, covering various facets that influence supplier selection. We'll dissect the mathematics behind this approach, offering insights into its application, possibly even through Python, for those inclined towards practical computation. Whether you're evaluating 3 suppliers or 10, this approach helps navigate the complexities of cost, quality, lead time, and environmental considerations. By integrating these factors, we aim to present a multi-criteria model that aids in identifying the most suitable supplier for your specific needs, incorporating both quantitative and qualitative factors, such as inventory holding costs and lead times, into the decision-making process. Initially, our approach to supplier selection is quantitative, focusing on material, freight, inventory, and administrative costs associated with each supplier. These factors are fundamental in assessing the total cost of sourcing from different suppliers, regardless of their global location. As we progress, we will also introduce qualitative factors into our model, including supplier quality, environmental practices, and reputation. This holistic approach ensures that decisions are not solely based on cost, but also reflect broader business values and sustainability considerations. The 4 quantitative factors to focus initially are material cost, freight cost, inventory cost, and administrative cost. The evolving nature of global supply chains challenges us to rethink traditional practices, considering both the benefits of local sourcing and the complexities of global procurement. Through this session, we aim to equip you with a versatile framework for supplier selection that is applicable to both domestic and international contexts. In this segment, we delve deeper into the concept of material costs, a cornerstone of supplier selection. Material cost negotiation is straightforward on the surface. It involves agreeing on a price per unit for the provision of a product or service with suppliers. Let's consider D as your annual demand and P as the unit price per item. The product of D and P gives us the annual material costs. For example, if your organization requires 1,000 units annually and each unit costs $1, the total material cost is $1,000. Simple, right? Historically, the pursuit of minimizing P to reduce overall expenses led many to choose suppliers based almost solely on price. This approach, while seemingly effective in cutting costs, overlooks other critical factors that could impact the overall value and performance of the supply chain. Instances abound where focusing solely on the lowest price did not equate to the best value, underscoring the necessity for a broader perspective that accounts for quality, reliability, and long-term partnerships. Freight costs represent another pivotal factor in supplier selection, characterized by a complex array of variables, including supplier location, shipment size, and mode of transportation. The method of shipment plays a significant role in determining cost. For example, bulk items shipped from Asia are typically transported in containers on ships, leveraging economies of scale. Conversely, sensitive products such as active pharmaceutical ingredients might necessitate air freight due to strict expiration dates or temperature control requirements, despite the higher cost. The distinction between full truckload (TL) and less than truckload (LTL) shipments is crucial. Opting for TL shipments, where the entire truck is used for one's goods, generally results in lower costs per pound compared to LTL shipments, which consolidate cargo from multiple shippers. While air transport is the most expensive option, it's sometimes indispensable for urgent or high-value shipments. Rail, on the other hand, offers an efficient and cost-effective means for transporting bulk goods like coal, steel, and other mined materials, echoing its historical significance and ongoing relevance in supply chain logistics. Through these examples, we see the intricate balance between cost, speed, and reliability in logistics decisions, emphasizing the need for a strategic approach to freight cost management within the broader context of supplier selection. In our ongoing discussion about supplier selection criteria, we now turn our focus to inventory costs. As we've previously discussed, understanding inventory cost is crucial. It's influenced by shipping quantities and lead times, with a lot size or order size, Q, playing a pivotal role in determining the cycle inventory a buyer must maintain. Recall the Q/2 assumption, which helps us estimate the average inventory level. This is visualized through the sawtooth inventory model, where inventory levels drop until replenishment, reflecting the cyclical nature of order and depletion. The intersection at the halfway point represents our average Q/2. Additionally, the combination of lead time and average demand per day or week dictates the level of pipeline inventory, assuming a constant lead time. This intricate balance of cycle and pipeline inventories forms the basis for our inventory cost considerations. Inventory costs are essentially the cost of holding inventory versus the cost of running out of stock, balanced against the need to meet customer demand efficiently. They are subject to variation based on several factors, including supplier location and the frequency of shipments. For instance, full truckload (TL) shipments typically offer a lower cost per pound compared to less than truckload (LTL) shipments. This distinction underscores the importance of strategic shipment planning and the selection of logistics partners, as the choice between TL and LTL can significantly impact overall inventory carrying costs. Some other factors include demand forecasting, lead time, and economic order quantity. Accurate demand forecasting helps optimize inventory levels, preventing overstocking or understocking of inventory. The lead time is the amount of time it takes to receive an order after it is placed. The longer the lead time, the more safety inventory stock you must hold. Determining the optimal order quantity that balances carrying costs and ordering costs will influence your inventory costs. These considerations are integral to optimizing supply chain efficiency and cost effectiveness. Delving deeper into the specifics of inventory holding costs, we revisit the formula incorporating cycle and pipeline inventories. The annual holding cost equation, Q/2 for average inventory, plus D times L for pipeline inventory, captures the total inventory cost. Here, D represents the average demand, L the lead time, and H the holding cost rate, derived from our previous discussions on inventory costs. This formula highlights the financial impact of inventory decisions, emphasizing the need to consider both cycle stock and the goods in transit when managing supply chain expenses. Through understanding and applying these principles, businesses can more effectively control their inventory-related costs, contributing to overall supply chain optimization. In this segment, we explore administrative costs, a crucial component of our total cost analysis in supply chain management. Administrative costs encompass the expenses associated with managing supplier contracts, including the time and resources spent on frequent interactions with suppliers. These interactions can range from digital communication, such as video conferencing through platforms like Zoom or Teams, to potentially in-person visits, which may be necessary even for suppliers located thousands of miles away. The encompassed costs include labour, managerial, travel expenses, and other variable costs stemming from supplier interactions. Such administrative efforts are pivotal for maintaining effective supply chain operations, highlighting the importance of accounting for these costs when selecting suppliers. Building upon the components discussed, including material, freight, inventory, and administrative costs, we now present a comprehensive view of the total annual cost, or TC. This total cost model integrates these varied elements, illustrating the cumulative financial impact on supply chain management. Initially, we focus on 4 primary categories: material costs, P times D, reflecting price times demand; freight costs, inventory holding costs, represented by Q/2 for cycle stock and D times L for pipeline inventory; and administrative costs. Together, these components form the TC, providing a foundational model for evaluating and selecting suppliers. As we proceed, we may expand this model to incorporate additional factors, further refining our approach to supplier selection and emphasizing the importance of a holistic view in supply chain cost management. Let's dive into a practical application of our total cost model to understand how it guides decision-making in supplier selection. We'll employ a formula that integrates material, freight, inventory, and administrative costs, applying it to different suppliers, supplier A through D as examples. The goal is to identify which supplier offers the lowest total cost, taking into account various order quantities and their impact on freight costs. Consider Excel Pharma, a company that manufactures drugs for controlling diabetes, seeking new sources for a key semi-processed raw material used in its most popular treatment. Excel Pharma is evaluating 3 potential suppliers, each located in a different part of the world, a common scenario in today's global supply chain environment. The annual requirement for this raw material is £30,000. The question arises, should Excel order all £30,000 at once or in smaller quantities, such as £10,000 3 times a year or £5,000 6 times a year? The company operates 250 business days a year, using an annual holding cost rate equal to 20% of the item's value. Your task is to analyze the data for each supplier, considering the total cost equation: material cost, P times D, plus freight cost, plus holding cost, Q/2 plus D times L, with D bar being the average daily demand and L the lead time, plus administrative costs. This example will challenge you to apply the total cost model to a real-world scenario, assessing the financial implications of different ordering strategies and supplier choices.
Let's dissect the freight cost data we've collected, an essential component of our total cost analysis. This data illustrates the annual freight costs associated with different shipping quantities for Excel Pharma, our case study company focused on diabetes medication. Considering the annual requirement of £30,000 of a key semi-processed raw material, we evaluate various shipping lot sizes to determine the most cost-effective approach. £1,000 shipments with a need for £30,000 annually, this implies 30 orders per year. £2,000 shipments, this reduces the order frequency to 15 per year. £3,000 shipments, here we only need 10 orders per year to meet the annual requirement. These calculations provide a clear view of how shipping quantity impacts freight costs, demonstrating the need for strategic planning in order size to optimize supply chain expenses. Excel Pharma is considering 3 suppliers located across the globe: Belfast in Ireland, Hong Kong, and Shreveport in Louisiana, USA. Each location presents its own set of logistics challenges and cost implications, making this analysis crucial for determining the most cost-efficient supplier and shipment strategy. Considering Excel Pharma evaluating suppliers for a semi-processed raw material essential for its diabetes medication, the complexity of this decision involves analysing various costs across potential suppliers located globally. We've identified suppliers from Belfast, Hong Kong, and Shreveport, Louisiana. Each presents unique cost factors, shipping costs, which, as expected, are lower for domestic suppliers like Shreveport, price per pound, with Shreveport offering the lowest rate, inventory carrying costs, lead times varying significantly among locations, and administrative costs, highest for Hong Kong due to distance and possibly other factors such as communication barriers or additional oversight requirements. To systematically approach this, we'll calculate total annual costs for 3 different order sizes: £1,000, £2,000 and £3,000 across all suppliers. This yields 9 distinct scenarios to consider, each with its freight, inventory and administrative cost implications. Such detailed analysis allows us to pinpoint the most cost-effective order size and supplier combination. Given the annual requirements, business operation days and holding cost percentage, we're equipped to construct a model that incorporates these variables into the total cost equation. This model will enable us to plug and chug, inputting data to calculate and compare total costs across scenarios. Whether using Excel, a calculator or Python for this task, the objective is clear. Identify the supplier offering the lowest annual total cost for XL Pharma's raw material needs. This exercise not only exemplifies the application of theoretical concepts to real-world scenarios, but also emphasises the importance of a comprehensive approach in supplier selection, considering both quantitative and qualitative factors to make informed decisions. Let's focus on a single scenario for Belfast, analysing a £1,000 shipment to understand how the equation works. This process will illuminate the broader methodology that can be applied using Python for efficiency and accuracy across all potential supplier scenarios. To begin, we determine the average daily requirements, D bar, by dividing the annual need of £30,000 by the number of working days in the year, 250, resulting in £120 per day. The total annual cost, TC, equation, which includes material, freight, inventory and administrative costs, guides our calculations. Average requirements per day equals D equals 30,000 / 250 equals 120. Total annual cost equals PD plus freight costs plus brackets Q / 2 plus DL n brackets H plus administrative costs. Material cost. For Belfast, the price per pound is $50. Multiplying this by the annual demand of £30,000 gives us a material cost of $1.5 million. Freight cost. For £1,000 shipments, the cost is $38,000 annually. Inventory cost. Calculating this involves a Q / 2 formula, plus the product of D bar, 120, and the lead time, 16 days from Belfast, factoring in the holding cost rate of 20% of the item's value, which translates to $10 per pound. Administrative cost. For Belfast, this is estimated at $280,000 annually. By adding these components, we arrive at a total annual cost for purchasing £1,000 shipments from Belfast. This example, whilst focused on a single scenario, forms the basis for expanding our analysis across different shipment sizes and suppliers, totaling 9 unique calculations. Through this approach, we can identify the most cost-effective supplier and shipment strategy, using either a spreadsheet for simplicity or Python for enhanced analytical capabilities. Spreadsheet setup for total cost analysis. In this segment, we transition our theoretical model into a practical application by setting up a spreadsheet. This approach allows us to visualize and calculate the total annual cost for different shipment sizes and suppliers, providing a clear comparison to aid in decision-making. For instance, we've already calculated the total annual cost for Belfast with £1,000 shipments as $1,842,000. This value serves as a benchmark for our analysis. However, our goal is to assess all 9 scenarios covering £1,000, £2,000 and £3,000 shipments for each of the 3 suppliers, Belfast, Hong Kong and Shreveport. The spreadsheet is structured to include columns for each cost component, material, freight, inventory and administrative costs, across the various shipment sizes and suppliers. By inputting the specific values into these columns, we can automate the calculation of total costs, leveraging Excel's absolute referencing feature to ensure consistency in our formulas. This setup not only streamlines the process, but also highlights the impact of order size and supplier location on the overall cost. With all values laid out, the next step involves verifying these calculations in Python, offering a more dynamic and scalable method for analysis. Whether through a spreadsheet or Python, the aim is to identify the most cost-effective supplier and shipment strategy, ensuring optimal supply chain efficiency. In this phase of our analysis for Excel Pharma, we transition from spreadsheet calculations to a Python-based approach. This method not only streamlines the process, but also offers flexibility in handling complex data and scenarios. Let's walk through the steps of setting up our Python environment and executing the total cost analysis. Python setup. We start by importing necessary libraries, NumPy for numerical operations and matplotlib for visualization. These tools are fundamental for data analysis and graphical representation of our results. Variable declaration. Annual demand A, set to £30,000, representing the yearly requirement for the raw material. Business days B, fixed at 250 days per year, reflecting the operational calendar. Average daily demand D bar, calculated by dividing the annual demand by the number of business days, resulting in £120 per day. Interest rate, assumed at 20%, 0.2, which will be applied in the calculation of holding costs. Array creation for each location. Arrays are defined to represent the total cost to ship, based on the order quantity for each supplier location. This includes different shipment sizes, £1,000, £2,000, £3,000, and captures the dynamic nature of freight costs. Price and lead time. We define arrays for the unit price per supplier and the lead times for shipments, which are crucial in calculating the total cost. Carrying cost calculation. Utilising NumPy, we calculate the carrying cost by multiplying the price by the interest rate, factoring in the cost of holding inventory over time. Defining a local function. To encapsulate the total cost calculation, we create a local function. This function will iteratively calculate the total cost for different suppliers and order sizes, enabling a comprehensive comparison. By systematically applying these steps in Python, we can efficiently evaluate the total annual costs across various scenarios. This not only demonstrates the power of programming in supply chain analysis, but also provides Excel Pharma with actionable insights to optimize its supplier selection strategy. The ultimate goal is to identify the supplier that offers the lowest total cost, thereby enhancing the company's overall supply chain efficiency.
In our journey to optimize supplier selection through total cost analysis, we now leverage Python's powerful programming capabilities. Python allows us to automate complex calculations, ensuring both accuracy and efficiency in our analysis. For Excel Pharma scenario, we'll create a custom function to calculate total costs, taking into account various factors such as supplier freight costs and order quantities. We begin by importing essential libraries, NumPy for mathematical operations and matplotlib for potential data visualization. The next step involves defining our key variables: the annual demand, A, the number of business days per year, B, and the average daily demand, D, calculated by dividing A by B. With these variables in place, we construct arrays representing the total shipping costs for different order quantities across our suppliers: Belfast, Hong Kong, and Shreveport. This setup allows us to systematically evaluate the impact of shipment size and supplier selection on total costs. Continuing our Python-based analysis, we focus on the implementation of a local function named TC designed to calculate the total costs for each supplier and order size scenario. This function requires two inputs: the supplier's annual freight cost as an array and an index to iterate through different shipment sizes and suppliers. By defining this function, we can easily calculate total costs for all 9 scenarios without redundant code, enhancing both the clarity and maintainability of our analysis. We illustrate the function's application using a loop which systematically calculates total costs for £1,000, £2,000 and £3,000 shipments from each supplier. This methodology not only simplifies the calculation process, but also provides a scalable framework for analysing additional suppliers or different cost factors in the future. By harnessing Python's capabilities, we enable a dynamic and comprehensive approach to supplier selection, grounded in accurate and detailed cost analysis. After executing our Python code to calculate the total cost for XL Pharma's supplier selection, we proceed to visualize these results. Visualization is a powerful tool for interpreting complex data, allowing us to discern patterns and make informed decisions more effectively. We start by plotting the total cost for each supplier across different shipping quantities. To do this, we utilize matplotlib, a versatile plotting library in Python. By plotting a scatter graph, we map the shipping quantities on the horizontal axis against the total costs on the vertical axis. This visualization includes data points for all 3 suppliers, Belfast, Hong Kong and Shreveport. In our graph, each supplier is represented by a different color. Interestingly, in some analyses, these lines might intersect, indicating a change in the most cost-effective supplier at certain order sizes. However, for XL Pharma's scenario, the plot reveals a consistent pattern. The domestic supplier, represented by green, consistently offers the lowest total cost across all shipment sizes. This finding underscores the potential advantages of domestic sourcing in certain contexts. To enhance the graph, we add titles, labels for the X and Y axes, and a legend to identify each supplier. Such graphical representation not only simplifies the comparison of total costs, but also highlights the impact of shipping quantity on supplier selection. Although we chose not to connect the data points with lines, doing so could further illustrate the relationship between order size and total costs for those interested in a more detailed analysis. This graphical analysis is not just limited to the current set of suppliers. The methodology can easily be extended to include additional suppliers, offering a scalable tool for supply chain management decisions. Through this exercise, we demonstrate the power of combining Python programming with data visualization to enhance decision-making in supply chain management. In our comprehensive analysis of supplier selection for XL Pharma, we focus primarily on quantifiable costs: administrative, holding, freight and purchase costs. However, supply chain management transcends beyond mere numbers. It's crucial to consider the broader impact of our choices, which leads us to incorporate qualitative factors into our decision-making process. Firstly, supplier quality cannot be overstated. The reliability and consistency of materials directly influence our final product's integrity. Therefore, we propose a qualitative assessment ranking suppliers on a scale from 1 to 10 based on their material quality. Environmental impact is another pivotal consideration. As a responsible corporation, we aim to minimize our ecological footprint. Suppliers will be evaluated on their sustainability practices and environmental policies, again using a 1 to 10 scale. One form of this is green purchasing, identifying, assessing and managing the flow of environmental waste and finding ways to reduce it and minimize its impact on the environment. Furthermore, factors influencing customer service, such as inventory management, lead times and on-time delivery, are essential. Efficient inventory management and shorter lead times enhance customer satisfaction, reducing the overall cost to serve. To illustrate, let's revisit XL Pharma's analysis, now considering these additional dimensions. Assuming Shreveport offers the lowest cost based on our initial model, we then integrate our qualitative assessments. If we assign Shreveport a score of 9 for environmental practices, but only 6 for material quality, how does it compare to Belfast and Hong Kong across these broader criteria? By extending our model to encompass these qualitative factors, we offer a more holistic view of supplier selection. This approach not only aligns with XL Pharma's operational efficiency goals, but also its commitment to quality, sustainability, and customer satisfaction. In refining our total cost analysis for XL Pharma, we've integrated additional qualitative factors to provide a more holistic evaluation of our suppliers. Recognizing that cost isn't the sole determinant of value, we've introduced assessments for quality of suppliers' materials, environmental impact, and factors influencing customer service, such as on-time delivery and inventory management. To operationalize these considerations, we've employed a weighted scoring system. Each supplier is scored on a scale from 1 to 10 across these dimensions, with 10 indicating superior performance. The scores are as follows. Total cost. We've maintained our quantitative analysis as a foundational element, assigning it a weight reflective of its importance. On-time delivery. Given a weight due its critical role in maintaining operational efficiency and customer satisfaction. Consistent quality. Heavily weighted to reflect the impact of material quality on our final product. Environmental impact. Assigned a weight to underscore our commitment to sustainability. These scores are then aggregated according to their respective weights, culminating in a comprehensive score that guides our supplier selection process. For instance, if Shreveport excels in total cost efficiency but has room for improvement in environmental practices, its overall score would reflect these nuances. This enhanced model allows us to make more informed, balanced decisions, taking into account not only the economic, but also the social and environmental ramifications of our supplier relationships. Which is now the best supplier to select? Other possible factors not shown here include annual sales, reputation partnerships, IP protection, labour uncertainty, political instability, similar products, border restrictions, and strength of supplier value stream. In this segment, we delve into the creation of a preference matrix for XL Pharma's supplier evaluation process. Our approach expands beyond the quantitative analysis, incorporating qualitative factors that significantly influence supplier selection decisions. We've identified crucial criteria such as on-time delivery, consistent quality, environmental impact, and potentially others like intellectual property protection and political stability. Each factor is critically evaluated, assigning scores on a scale from 1 to 10, reflecting each supplier's performance. For example, we consider the total cost where Shreveport excels, granting it a high score. Management assigns weights to these criteria, ensuring the total adds up to 100 points. This balanced approach allows us to quantitatively assess suppliers, blending both cost-related and qualitative factors into our decision-making process. Utilizing Python, we import the Pandas library to structure our data efficiently. We create a data frame, inputting scores for criteria such as total cost, on-time delivery, consistent quality, and environmental impact across our suppliers, Belfast, Hong Kong, and Shreveport. Each criterion is weighted according to its importance in our overall strategy, ensuring a comprehensive evaluation. The final analysis yields total weighted scores for each supplier, guiding us towards the most advantageous partnership. This method not only identifies the most cost-effective option, but also aligns with XL Pharma's strategic objectives and ethical considerations. This preference matrix serves as a testament to the power of integrating qualitative measures into supplier selection, showcasing a methodical approach to making informed, balanced decisions in supply chain management. In this segment, we present a student practice problem to solidify your understanding of calculating annual holding costs within supply chain management. This exercise mirrors the concept we've explored earlier, applying them to a new dataset to ensure you grasp the application of these principles in a real-world context. Labware Company is in the process of selecting a supplier for 1,000 milliliter beakers, anticipating annual sales of 100,000 units. The company operates a warehouse 50 weeks a year, 5 days a week, with an annual holding cost of 20% of the beaker's cost. Your task is to calculate the annual holding cost per unit. This calculation involves the price per unit multiplied by the interest rate, which is set at 20% or 0.2. Despite different scenarios, the formula remains consistent due to the uniform price per unit. You're provided with data on 2 glassware suppliers, Bradley Solutions and Alexander Limited, both reputable manufacturers of low-form, heavy-duty glass beakers. The challenge involves analysing the provided data to determine which supplier offers the lowest annual cost to Southern Labware and recommending an optimal shipping quantity. As you work through this problem, consider the steps involved in calculating the annual holding cost and apply this to the context of Southern Labware's operational needs and supplier options. This exercise not only tests your understanding of supply chain financial metrics, but also encourages you to engage critically with data to make informed decisions. Southern Labware is in search of a supplier for 1,000 milliliter beakers, with an annual demand forecast of 100,000 units. Your task is to analyse the combined data for 2 potential suppliers, Bradley Solutions and Alexander Limited, renowned for their high-quality, low-form heavy-duty glass beakers. Unlike previous examples, here we present the freight costs alongside other critical data within a single table for clarity. Consider the annual holding cost per unit, applying the formula that involves the price per unit multiplied by a 20% interest rate. Reflect on which supplier offers the most cost-effective solution for Southern Labware, and recommend an optimal shipping quantity based on your analysis. Building upon the initial task, we now introduce a rating scheme to deepen our analysis. This scheme evaluates suppliers across 4 key dimensions: total cost, on-time delivery, product quality, and environmental impact. Each criterion is scored on a scale from 1 to 10, guiding us towards a comprehensive assessment of each supplier's overall value. Your challenge is to apply this rating scheme to our practice problem, considering both Bradley Solutions and Alexander Limited. Based on the combined quantitative and qualitative evaluation, determine which supplier emerges as the most advantageous for Southern Labware. This exercise not only tests your ability to calculate and analyse financial metrics, but also encourages you to consider broader factors that influence supplier selection. It's an opportunity to engage critically with the data, apply theoretical knowledge to a practical scenario, and make informed recommendations. As we conclude today's session, remember that this practice problem is a stepping stone in your journey to mastering supply chain management. Through exercises like these, you develop critical thinking and analytical skills vital for navigating the complexities of the field. We look forward to our next meeting, where we'll explore the concept of reverse logistics, further expanding our understanding of supply chain management. Thank you for your dedication and hard work.